Good afternoon, I'm Mr. Precella, and today we're going to look at inverse functions with my Math 13-14 class. And let's see, I need to talk a little bit before we look at any of the homework problems. Remember, we said that is that focused? Yes, there. We said that a function was a set of ordered pairs of which there was no repeated x value, okay? Formerly we said each x could be assigned to one and only one y value. You can't have an x value assigned to two different numbers. We said that repeated y values were okay. We said that repeated y values were okay, and the relation could still be a function if you have repeated y values, but there's a special type of function called a one-to-one function. One-to-one function means it's a function of which there's no repeated y values. It is a function with no repeated y values. We're going to look at, well, it's easy to look at a function if it's just a list of ordered pairs. If you see the same y value twice, then it's not one-to-one. Well, how can we tell if a graph of a function is one-to-one? So we'll look, first of all, I'll say ordered pairs. Ordered pairs. You can tell if it's one-to-one just by looking at the y values. There's no repeated y value. No repeated y's. Graphically, a graphical interpretation. Oh, let's see. Let's look at this graph here. I'm going to draw a graph. I'm just making it up. Let me move my paper up. And I'm going to use a quadratic function. A parabola. That's not a very good parabola, but remember it should be a mirror. The left side should be a mirror image of the right side. Well, I messed it up a little bit. What do y'all think? This is a quadratic function. Oh, what do y'all think? Y'all think that has repeated y values? I think, look right here at the x-axis. Look at this point right here on the x-axis. I don't know what that x value is, but I know the x value is positive. What's the y value at that point? 0, okay. What about this ordered pair? The x value is negative. What's the y value? 0. I think we have repeated y values right there. Repeated y values, so this is not one-to-one. We know that a quadratic function has to have, what's the biggest exponent in a quadratic function? X squared. I agree. So the general form would be y equals ax squared plus bx plus c. Generally, those quadratic expressions cannot be one-to-one because there's something called the horizontal line test. To determine if a graph represents a function, you have the vertical line test. To determine one-to-oneness, you have a horizontal line test. If you can draw a horizontal line so that it hits the graph in two spots, it is not one-to-one. So To determine a function, you use vertical line test. To determine if it's one-to-one, you use what's called the horizontal line test. And I'm going to go back to this notion of a quadratic function. It's the even exponents that mess up things, because whether you take a positive 5 or a negative 5, when you raise it to an even power, what are you going to get? What are you going to get? Well, you're going to get a positive sign, whether it's positive 5 or negative 5. When you square it, you're going to get a positive 25. It's those even exponents that cause these repeated y values. So when you're looking at an equation, and for an equation, not one-to-one, I can think of two different things that we've graphed this semester that would not be classified as one-to-one. One of them, it's this picture right here, the U-shaped figure, those even exponents. If you see that the equation has even exponents, you should start thinking that it's probably not going to be one-to-one. I remember another graph we drew this semester. It wasn't a U, it was a sharp V. Do I remember that? Absolute value. Good. Absolute values. An absolute value, it'll certainly fail that horizontal line test. So the second thing to be on the lookout, if your equation has absolute values, it's not going to be one-to-one. So I'll say absolute values. And while we're on the roll, I think I'll keep on going for a while. I don't want to get timed out here, so let's do a couple of these problems. The first two problems, and we can do it, you're not going to need any to show any work. I think you'll be able to answer them without any work. Is this function one-to-one? You'll see the blue graph, that blue diagonal line. Could you draw a horizontal line so that it hits it twice?
No.
No. So yes, this thing is one-to-one. No work to show, just is it or isn't it one-to-one? And yes, it is. What about that? Realize some people will say, oh, it looks like, I think it's going to turn around. No, it isn't. If it's going to turn around and start going up like that example I made, then they have to show that. As it is, it's just continuing to go down real slowly. It's decreasing. Is this one-to-one?
Yes.
Yes, it is. I was thinking this was going to be a no, actually, but yes, it is. It stands to reason, one yes and one no. Okay, and that's enough for now. Let's consider these two functions. I have the function f, and it's going to contain the ordered pairs 0, 9, -1, 7, 5, 15. Just 3 ordered pairs, that's good enough. And I'm going to skip a line here. I'm going to make up another function. Here's the function. Oh, by the way, notice there's no repeated x value, so that is a function. Now here's g. G is my second function. It'll have the ordered pairs 2, 4, comma, -2, 4, and how about 5, 25? I'm feeling lazy today. I'm just using 3 ordered pairs. So I've made up two sets of ordered pairs, both of which are functions. Notice every x value is different in both of these things. Now, the inverse of a function is the set of ordered pairs you get when you swap the x and y coordinates. We have a special notation for inverse. It looks like a little exponent, but it isn't. The inverse of f is denoted the function name with a little superscript of -1. It looks like it's saying f to the -1 power, but it isn't. If you have a function name and that little -1 there, that says you're reversing the ordered pairs. 0, 9 becomes 9, 0. -1, 7 becomes 7, -1. And 5, 15 becomes 15, 5. You tell me which ordered pairs will be in the inverse of G. G inverse. 2, 4 is going to become 4, 2. I agree. -2, 4 will become 4, -2. And 5, 25 becomes 25, 5. So, hey, look at that. Is G inverse a function? It's no longer, G is a function. Notice there's no repeated x values, but when we form the inverse, we now have repeated x values, those 4s. But what went wrong? F inverse is a function, 9, 7, 15, they're all different. So what went wrong here? What's the fundamental difference between F and G? It's the step we start. No, just in general. I'm looking for just a general remark based on what we were talking about a few minutes ago. 1-to-1 has no repeated y values. That's the difference. F is 1-to-1. Notice those y values are different. F is 1-to-1. G is not 1-to-1. That's fine. G doesn't have to. It can be a function and have the same y value, but when you form the inverse, those repeated y's, which are okay, become repeated x values. G is not 1-to-1. And because of that, G inverse, you can find the inverse, it's just not a function.
And the F inverse is 1-to-1?
F inverse is 1-to-1, and a 1-to-1 function, and F is. If F is a 1-to-1 function, then its inverse is a 1-to-1 function. Let's state this. How about we say it like this? Only 1-to-1 functions have inverses that are functions. Function's got to be 1-to-1 in order for its inverse to be function. You can still find the inverse of something that's not 1-to-1. It's just not going to be a function, though. And in this course, we're only interested in finding the inverse of 1-to-1 functions. Let's keep going. Okay. We're looking at number 3. This should get us through number 7, I think. Decide whether the given functions are inverses. I'm not sure this is something y'all need to write down. Okay? It takes longer to write it down than it does to answer the question. If they're inverses, maybe we should have written, I said it, but maybe I should have written it down. Inverses, it's just swapping x and y. It just swaps x and y. The ordered pairs are reversed. So, and okay. Are these functions inverses? Negative 4, 3, that's the first ordered pair. Well, if it's being swapped, it'd have to become a 3, negative 4. That's what we have. Negative 5, negative 1. If you reverse the x and y, yes, negative 1, negative 5. What about 2, negative 5? It should become negative 5, 2, yes. What about 5, negative 2? It should become, yeah. So these things are inverses. Number 4, are the functions inverses? Here they're just writing them out as ordered pairs rather than a table the way we were doing the other one. What do y'all think? Are those inverses? Are the ordered pairs reversed? Yes, they are. Negative 3, negative 4. You have to look carefully because I know they could just drop a little negative sign and it's hard to spot. 2, 3, yes, yes, yes. So this is another yes. Now, if the following defines a one-to-one function, they want us to find the inverse. If it doesn't, write not one-to-one. I'll write this problem down. Okay, let me write it down. This is number 5, and we have the function with the ordered pairs 7, 11, negative 19, negative 18, and negative 3, 12. Okay, so is this one-to-one? Before we do anything else, we better decide. Is it one-to-one? Look at those y coordinates. What do you think? Yes, it is one-to-one, so we better find the inverse. It is one-to-one. I'll put a little check to indicate that it's one-to-one. Now we're going to find the inverse. 7, 11 becomes what ordered pair? 11, 7. Negative 19, negative 18 becomes, and the last order pair, so here's what we're looking for. Let's switch back to the, okay, so we need 11, 7, negative, I don't think it's B, I think it's C, is that it? Any questions there? Okay, well it can't stay that easy forever, can it? This is number 6. Actually, this is one of the easier assignments, according to what students say. Negative 6, negative 8, 16, negative 8, and 13, 9. Let's switch. There they are. Negative 6, negative 8, 16, negative 8, and 13, 9. What did you say, Dale? Not one-to-one. Notice we have repeated y values there. So not one-to-one. And here's a notation that we like to use for one-to-one. Instead of writing out the words 1 to 1, it looks like 1 minus 1, but that's a shorthand notation for one-to-one. That's accepted in mathematical circles. So out of laziness, I might be doing write it like that. Some. So we go over here to number 6, and we select not one-to-one. I want to warn you, I bet you one of these, if you just notice that that was not one-to-one, you might have chosen B. Negative 8, negative 6, negative 8, 16, and 13, 9. they have the inverse there, but they don't want you to find the inverse if the function is not 1 to 1. So be careful there. Any questions? Number 7. Oh, same problem. Let's see, number 7. Let me write it down. Same instructions, not the same problem. Let's see, -6, -2, 48, 12, -8, -6, and -9, -3. Oh, goodness. That's sort of messy. Can y'all read that? -9, oh, y'all can't read it. Well, let me make sure I don't miscopy anything. -6, -2, 48, 12, -8, -6, and -9, -3. Okay. There it is. -9, -3. It's sort of messy, but hopefully y'all can read it. Is it 1 to 1? If it's 1 to 1, we have to find the inverse. So what did you say? Yes, it is. You're right. Every y value is different. So the function is 1 to 1. Now let's find the inverse. We just go through. -6, -2 becomes -2, -6, 12, 48. -6, -8, and -3, -9. So what is that? A, B, C, A, B, or C? Looks like B. Any questions up to this point? Okay. Remember that the domain of a function is the set of all numbers that are used for x values. And what do we call the set of all y values? The range. So let's find, I'm going to name this function f. I need a name for it. I'm going to call it f. So I'm going to keep using the same function that we have, but I'm through with number 7, okay? So I'm just going to say, consider the above function. Consider the above function f. That means this green thing is f inverse. Here's my question. What numbers are in the domain of f? Domain of f. Looking at my function f, which numbers are in the domain? I can't hear you. Oh, well, there's more than that. It'd be all the different x values. So -6. The domain is just the set of all numbers used as x values, and -9. What about the range of f? What's the range of f?
-2, 12, -6, -3.
Okay, so -2, 12, -6, and -3. I agree. -2, 12, -6, and -3. Now I have a point to all of this. Now I want to know the domain of f inverse. We found the domain of f and the range of f. What's the domain of f inverse? And we're looking at f inverse. This one here. What numbers are in the domain of f inverse? -2 and 12, -6 and, remember how we swapped the x's and y's. The x's in the original problem became y's, and the y's became x's. So we can convince ourselves pretty easily that the domain of f will have to equal the range of f inverse. What about the range of f? The y's in the original, what did they become? The domain of f inverse. The x's in the original function become y's in the new function. The y's in the original function become x's in the new function. Makes sense? It should be obvious because of the way that we swap the x's and the y's. Okay, so that means you're ready for number 8. Fill in the blanks. The domain of f is equal to the blank of f inverse, and the range of f is equal to the blank of domain of f inverse. The range of f, the original x's, are equal to what? The range. Pull down and select range. The original y's, the range of f, become what? The domain in the inverse. Any questions? When we're listing just a set of ordered pairs, we can tell, we can look and decide pretty easily what the domain, what the inverse is. We can tell easily if it's 1-to-1. Here's something, I think we need a algebraic definition of inverse function, and this goes back to something that we were doing the last 2 problems I think we had in the last assignment, if I remember correctly, where we found the compositions and everything reduced to x. And we're trying to get you ready for this formal definition here. The algebraic definition of inverse functions. Algebraic. Although you know the intuitive notion of an inverse, it's just swapping the x and the y. Algebraic definition of inverse functions. Let's assume f and g are 1-to-1 functions. F and G are said to be inverses if each of the following is true. One, f composed with g of x reduces to x for every x in the domain of g, and if you reverse the composition, g composed with f of x reduces to x for every x in the domain of f. If you can find the composition of the 2 functions and everything cancels out for x in both directions, then we say the functions are inverses. And I'm going to go back, I'm going to stop. I'm going to say that. I'm going to go back to what we were doing. I think it was 1 week ago today. Of course, I'm on a block page here. Let's see. Where were we? We were working with compositions. Here it is. Do I remember? Now remember these problems here? For the given pair of functions, find f composed with g of x and g composed with f of x. Then they asked, are they equal? And we said, usually they're not. But this is a special case. Everything in both directions, when you found the composition, they canceled out everything except for x. And in that event, f and g are inverses. Look back at the other one. Number 10, same instructions. Find their compositions. They both reduce to x. That means 4x minus 3 and 1/4 times x plus 3. Those are also inverses. Now remember doing that? Okay, then number 9. Let's go back to the assignment we're working on. Let's see, here it is, inverse functions, and number 9. Oh, I forgot about this one. I like this problem. I should have. Okay, this has nothing to do with what I just stated, okay? So let's do number 9. Number 9, let me write it down. Okay, if f has an inverse, and f of -3 is equal to 6, then f inverse of 6 is equal to blank. Okay, so let's push this up a little bit. Look at this original statement. F of -3 is equal to 6. Using that function notation, what number is the x value? -3 or +6? -3 is the x value. So you have the ordered pair, -3, 6. Now we're going to reverse it. In the inverse, the x value is 6. What does the y value have to be? -3. So if f of -3 is equal to 6, then f inverse of 6 is equal to 3. -3, thank you. Okay. -3. Now, let's look at number 10. This is what I was trying to get you ready for a moment ago when I stated the formal definition of inverse functions. If you have two functions and you're wondering, are these things inverses? You know how to find their compositions. Find the compositions the way you did in that assignment 1 week ago. If everything reduces to x, then great, they are functions. If something doesn't cancel out, then they are not functions. So let's write down number 10. They give us two functions. Oh, this looks sort of messy, doesn't it? Okay, let me write it down. Number 10, f of x is the rational function. That means it's a fraction. 2 on top and x minus 7 on the bottom. And g of x is equal to 2 over x and a plus 7. Determine whether the two given functions are inverses of each other. Well, they give us two functions. Let's find their compositions. If everything cancels out except for x in both directions, great, they are inverses. If you're left with stuff that won't cancel out, then they're not inverses. So let's find, do y'all remember how that function notation works? You take f composed with g. Fog and golf. Y'all remember that? Fog and golf?
Can you switch to me?
Oh, thanks for reminding. There. We were finding the compositions. We were trying to do it in as few steps as possible because that students have more success that way. We've noticed after 35 years of doing this stuff. 36, actually 37, but okay. F composed with G. You take G of X and you plug it into F. So you're taking this stuff, G of X, and you're plugging it in to F. So we're going to have a messy fraction. We have a 2 over, we have that in place of X, we're going to have that black stuff, 2 over X plus 7. What else do we have down there in the denominator? A minus 7. What we have here is called a compound fraction. It's a fraction that contains one or more additional fractions. Well, something's about to cancel out here very nicely. What is it? The 7 minus 7, that's gone. So all we have at this point is 2 over X. Some terminology. This blue fraction bar here, the one that you were plugging into, that's the major fraction bar. Any remaining fractions in the problem, those are minor fraction bars. What I like to do to simplify compound fractions is multiply above and below the major fraction bar by the minor denominator. The minor denominator, the denominator of the minor fraction is X. Let's multiply above and below by X. Multiply by X. Multiply by X. And remember, we're allowed to do that because we can multiply above and below by anything we want to, as long as it's not 0. You can't multiply above and below by 0 because then everything would become 0 over 0. Now look down here at the major denominator. I think right here something's about to cancel out. What is it? The X's are going to cancel out. So you have a 2x all over, what is it? Over 2. What's about to cancel out there? The 2's cancel, leaving us just X. Hey, that's good news. The composition F composed with G reduced just to X. Now to be sure that they're inverses, we better find G composed with F, because it is possible. You can find F composed with G and it reduces to X, but G the other direction doesn't. But it's highly unlikely. I'll tell you that much. If one of them reduces to X, and if this were a game in Vegas and I was having to bet, I'd bet that the reverse would also reduce to X. I wouldn't always win, but I'd walk away from the table with more money than I would have than I started with, okay? Because more times than not, if one of them reduces to X, the other direction reduces to X also. But let's go ahead and do it in the other direction now. G composed with F. G composed with F. That says, take F of X. Where are you going to plug F of X into? You plug it into G. So you're taking this blue stuff, the 2 over X minus 7, F of X, and you're plugging it in over here in place of that X. This one looks like it's going to be messier than the first one. So we're going to have the 2 and the major fraction bar. What are we going to have right here? A plus 7. You see the 2 fraction bar, you have the plus 7 on the right. In place of that X, we're writing that 2 over X minus 7. If these are inverses, and I think they probably are, Everything should cancel out except for that x right there. What's the minor denominator in this case? X minus 7, that's multiply. Let's multiply above and below by x minus 7. So we have an x minus 7 and an x minus 7. Working in the major denominator, working down here, what's about to cancel out? Now remember, you're trying to get stuff to cancel out. So resist the urge to distribute that too. If something's going to cancel, it's going to have to be in a factored form. So leave it as 2 times x minus 7. And what have we got left over in that denominator? That 2, the blue 2, and we still have that plus 7. If you had distributed that 2x minus 14, you couldn't do what I'm about to do right now. Here, that top is in factored form. I can cancel the 2's. So all I'm left with is x minus 7. And what else do I have stuck on there? A plus 7. And voila. Everything canceled out except for x. Therefore, we can conclude F and G are inverses. Correct. Any questions there? Okay, so we come over here. All we do is just select functions f and g are inverses of each other. Any questions there? So if we have two functions and we're wondering, are they inverses? You can find their compositions. If everything cancels out except for x, then they are functions. Suppose instead of a plus 7, this thing had been a plus 8. We would have had that minus 7 plus 8. We would have been stuck with a positive 1. We would have had something other than just an x, in which case they're not inverses. In order to be inverses, fog and golf have to cancel out everything except for x. The natural question is, how do you find an inverse? Okay, suppose they've just given us one function. How do we find the inverse? That's the natural next question. Now, we're only going to find inverses of one-to-one functions. So let's review something I wrote on the first page of notes today. For one-to-one functions, let me switch over. One-to-one functions we looked at functions in 3 different formats. One of them ordered pairs. If they're not one-to-one, but that we said that means there's no repeated y values. You just look at the ordered pairs. Do you have the same y value? If not, repeated. If not, then they're one-to-one. No repeated y values. We said something about graphs. If you're looking at a graph of a function, it's easy to determine if it's one-to-one. Use the horizontal line test. What if you have an algebraic equation, something with variables? I'm running out of room to move this up a little bit more. There. Algebraic equation. This third one is the important point that I'm trying to make. There. If an equation's not you expect an equation not to be one-to-one when there are even exponents, because with even exponents, say 10 and negative 10, when you square it, you get the same y value, a positive 100. So even exponents are a problem, and absolute values, I'll say, they're not, an algebraic equation is not one-to-one if it has even exponents or absolute values. And we can prove that just using the horizontal line test. And look back here at number 10. I claim f of x was 1-to-1. So was g of x. They're inverses, and you can look, when I looked there at f of x, I saw, well, there's no even exponents. It's just an x to the first power, no absolute value. So you just convince yourself, yeah, they're 1-to-1. What about g? Yeah, no even exponent, no absolute value. So both of those things are 1-to-1. So when we look at what they're asking us to do on number 11. They give us a function, and they say, if it's 1-to-1, they want us to find a formula for its inverse. Don't write this problem down yet, okay? Because I think I'll write down the recipe. There's a nice little recipe for finding the inverse, and I think I'll write that out. And I think y'all can help me. I think y'all can help me figure out how we're going to find the inverse of a 1-to-1 function. I'm going to write out to find and this isn't like the cut point process, okay? This is a short process, so don't start panicking. I can tell that's what Amy was thinking. She was like, oh, to find, let's see, to find the inverse of an algebraic function first of all, you need to verify that it's 1-to-1, because if it's not 1-to-1, then you don't want to bother finding the inverse. You'll select not a 1-to-1 function. Verify f is 1-to-1. Number 2, tell me in words. You have an intuitive notion of what an inverse function is. Tell me in words. What is that saying to do? What does an inverse do? Swap. There it is. Let's swap x and y. Everywhere you have an x, you're going to write a y. Everywhere you have a y, you're going to write an x. Swap x and y. At that point, you have a form of the inverse, but it's standard practice to have to write the inverse using inverse function notation, that little f with a little superscript of -1. So at this point, we'll solve for y. Once you solve for y, you're basically through with the problem. The last step, you'll replace y with the inverse function notation. Replace y with f inverse of x. But my lab will type the f inverse of x for you. You won't even have to hassle with the little superscript button, okay? They'll type f inverse of x equals, and so the thing you got on the other side when you solve for y, that'll be the answer you're looking for. This is a pretty short process. It's not a cut point process or solving square root equations process. So here we are, number 11. Let me write the problem down. f of x is equal to 6 over x plus 3. Determine whether the function is 1 to 1. If it is, find a formula for its inverse. So, first thing we got to do is, I claim this is 1 to 1. What do y'all think? Do you see any even exponents, say an x squared, x to the fourth? Do you see any absolute values? No, so you just convince yourself. There's a way to formally go about proving that it's 1 to 1, but we don't have to do that. Not in a college, a freshman level algebra course. All we got to do is just convince ourselves, yeah, there's not going to be repeated y values. So I'll write it down. I'm going to say f is 1 to 1, y, no even exponents, no absolute values. So that's step number 1. Now I'm going to come over here and I'll say, yes, it's 1 to 1. Now, I want you to find that if it had not been 1 to 1, you'd select the function's not 1 to 1 and you'd be through. But since it is 1 to 1, we have to find the inverse. And you see what I said? They're giving you the f inverse of x. So all we really have to do, swap the x's and y's and solve for y. The step on the other side of the y will be the inverse function. So here we go, second step. We got to swap x and y. Wait a minute. I don't even see the letter y here. What's acting like y? F of x is acting like y. That notation there is just a fancy way of saying y. So now we're going to swap. The y will become x. The x will become, the y became x. The x becomes, no, y, just a y. Well, which is f of x? You're right, okay? Now that I thought about what you said, but generally we don't want to be multiplying f of x and stuff like that. The y became x, the x became y. So we did the second step. We swapped x and y. Now we need to solve for y. That means we needed y by itself on one side without anything else. We need that y by itself. We got to get it out of the denominator. You know what I think? I'm going to treat this x as an x over 1. We're ready for step number 3. We're going to solve for y. Why did I write that as x over 1? What am I thinking I'm going to do?
Multiply.
Cross multiply. Take. You could just say multiply both sides by y plus 3, but when you can get it as a fraction equals a fraction, if you can write it as a proportion, students seem to like that better. You take x times y plus 3 is equal to, x times y plus 3 is equal to there, 6 times 1 is 6. I think I'm going to get rid of those parentheses. You'll have an xy plus, distributing the x, 3x equals 6. We want y by itself. So what do you think I'm going to do to that plus 3x?
Subtract it.
Subtract it, so I'll have xy equals 6 minus 3x. There's only one step left to get y by itself. I couldn't hear you.
Divide by x.
Divide by x. The x's cancel, and you're left with just y equals 6 minus 3x all over x. Do not start trying to cancel here. The only way you're going to be able to cancel is if you split it up. 6 over x minus 3x over x. We don't have to do that. Just get y by itself. I'm going to stop right there. Well, technically we have that fourth step. Replace y with the f inverse of x. Technically we had that fourth step, but remember I said my lab is typing the f inverse of x notation for you, so you can stop after step 3. Once you get y by itself on one side, the step on the other side is the inverse. Any questions there? The thing that poses problems, although there's not that many student problems with this process, but if there is, it's the fact you're swapping x and y, and people start off saying, well, I don't see a y. Remember, f of x is the same thing as the single letter y. So just mark out that f of x and think of it as a y. Y becomes x becomes y, solve for y. So we come over here. The first thing I'll do is click on my fraction hot button. On top I have a 6 minus 3x. And on bottom we have an x. Any questions here? Let's do another one. Determine whether the function is 1-to-1. If it is, find a formula for its inverse. F of x equals x cubed minus 1. Now, the first thing we need to decide, is it 1-to-1? What do y'all think? Yes, it's 1-to-1, but wait a minute, I see an exponent right there. It's an odd exponent. An odd exponent is fine. Odd? Okay, it is 1-to-1. So that's the first step. We convince ourselves that it's 1-to-1. No work, just look and convince yourself, yes, it's 1-to-1. And that means they want us to find the inverse. So here we go. Step number 2. We got to swap x and y. Well, what's acting like y in the original problem? F of x is just that fancy way of saying y. So, oh, wait a minute, thank you. There, thanks. F of x is that fancy way of saying y. So, y becomes x, and x becomes y. So we have x equals y cubed minus 1. This green pen isn't wanting to work. I better switch. Let's try this one. So we have x equals y cubed minus 1. Third step, we have to solve for y, and that's really the final step. Just get y by itself, then the other side is the inverse. We need to get y by itself. What do you think we'll do first? Add 1, I agree. That'll give me an x plus 1 is equal to y cubed. Then you realize what we're doing? We're using the inverse of the cube function to get rid of that cube. That cube root is the inverse of the cube function. When they're performed consecutively, they cancel out everything except the variable underneath there. So we're taking the, y'all remember doing this? Solving radical equations? We would use the fact that the cube and cube root would cancel each other out, but we didn't call them inverse functions then. Now we can say they're inverse functions. The cube and cube root cancel themselves out. So what have we got left on the right-hand side? Just y. And on the left, we have that cube root of x plus 1. Now, and this was step 3 here when we were solving for y. There's your answer. I'm not even going to bother with the 4th step. Not even going to bother with it. I'm just going to say, there it is. The thing on the other side is your answer. Any questions there? Okay, so we come over here. I'll click here. I'm going to type in my answer. What do I have to do? Is this what I want? And I want the one that has the little blue box. Y'all see this other radical, the nth root? What goes up there as the index? That's where you type your 3. Then you click underneath that radical and you type in your x plus 1. Any questions there? I think number 13, oh, it's circles. Completing the square with circles. Have we done all of the ones? Is this the last? I think this is the last one. I think that's the last new material. Did we do everything? Oh, I did a click on these media here and there, but yeah. Any questions? This isn't too bad, in my opinion. And based on student responses in the past, I feel like I must have done something wrong because the other videos are an hour 15 minutes, and this is just an hour 1 minute. But I did every problem. That's what I was looking at. I didn't skip any. Oh, wait a minute. Let's make sure. Let me look. I did all 12 problems, correct? The first few, we didn't write anything down. They were just yes/no questions. Yeah, that's it. Okay, well, any questions?
Nope.